Here is one more tool to observe a product of our design as a system or to model it as a system. The approach suggests a kind of generic criteria to tell if the design that we have is good or bad. The method was introduced by Professor So from MIT in the end of last century, and it has won its small but stable share in the toolkit of design methods or research topics by the time being. So it is easy to find original materials all on axiomatic design or further readings, because this short video delivers just the main ideas in the context of our course, Artificial Inventiveness. However, these ideas helped me several times in design projects, and that is why I am absolutely sure that it is worth learning. Basically, it's design evaluation criteria that places it near ideal final result concept or trends of engineering system evolution from theory of inventive problem solving. Indeed, these are mostly evaluation tools. They can be used to compare different design ideas and to tell which one is better according to trees, which one is more ideal, which one is more dynamic, more functional. We will also see that the contradiction can be observed in the kind of generalization of axiomatic design too. And if you have background in cybernetics or in system theory, the concept of axiomatic design will somehow resemble the idea of autonomy in multi-input, multi-output or me-more systems. There are two basic statements in axiomatic design. They are called axioms, although they are not really axioms in strict mathematical meaning of this word. These are rather two criterion or two indexes or two properties that system needs to have if it is called good. We will focus mostly on the first one. And the idea is the following. First, we define what do we want from our system, what are system outputs. We call them function requirements. Second, we define what we can change in the system, what are inputs to the system that we can vary or can change. They can be external signals to the system, control signals, or they can be parameters we can change in the design. We will call them design parameters. Professor So noticed that the design is optimal from his point of view if specific design parameter can be adjusted to satisfy its corresponding function requirement without affecting others. In other words, the system becomes autonomous. It falls apart into a set of scalar direct interactions from design parameter to function requirement. This idea can be easily given a mathematical illustration, if you are not afraid of mathematics, of course. If we have a vector of function requirements and we have a vector of design parameters, then what is between them could be called design matrix, a set of functions, a set of numbers. And if the matrix is full, there are no zeros in the matrix, then unfortunately by changing any input parameter we will affect all output parameters. Then the design is called coupled. If the matrix is diagonal, each function requirement can be adjusted by specific design parameter independently. And then design is called independent. That is good. And finally, the third case, if the design matrix has a kind of triangular topology, upper triangular or lower triangle, then it is called decoupled. In this case, each function requirement can be addressed, but the design sequence should be correct. Here is a classical example of evaluation of two designs from this perspective. There are two water taps. Which one you like better? So, function requirements are the same for both of them. We need water and we need certain temperature of water, so we need the flow of water and water temperature. But in the case of the first design, this kind of tap, the design parameters are vertical angle and horizontal angle of the handle. And the design matrix is diagonal. So the design is optimal or independent. And indeed, it's very nice from user perspective, isn't it? We can agree. In the second design, we have two valves, a kind of last century design. Design parameters are different, and there are left and right valves angles as the design parameters. Having rotated any of these valves, we can affect water temperature and the flow both. Then the design is called not optimal or coupled. The second axiom of Professor So can be used to compare independent designs. In other words, when multiple designs are found from axiom 1, then the best one could be found or chosen based on axiom 2. The best independent design is that one that requires minimal amount of information to be described. That's the axiom 2. My translation of this kind of academic statement to common sense language would be: the simpler, the better. The amount of information could be amount of drawings, amount of text, amount of numbers, amount of information in Shannon sense that you need in order to describe the design. It can be quantified and carefully calculated, or the concept can be used in a kind of qualitative manner. Now let us, for example, compare 3 tab designs in the picture. They're all independent. Which one you like better? They all are nice. But it's hard to give a measurable evaluation of, let's say, information needed to describe them. How many drawings we need, how many parts of them. But maybe the left one has slightly better chances to be called the simplest. So it would be chosen as the most suitable in accordance to axiom 2. We cannot help pointing out that this second axiom actually seems to be really similar, have similar meaning to the concept of ideal final result from theory of inventive problem solving trees. The simpler, the better. Small amount of parts, small amount of elements, small amount of subsystems. So, how does it all work? So we get a device, a product, or an interface we want to develop to improve. We focus on the interaction of this product or interface with the user, with the client, or with the operator. We define what do user or operator want or has to control in operation time. And these are function requirements. Then we check what the control inputs are to the current design. So what we can change, what we can vary, assign, tune in the design to address these required outputs. And these are design parameters. If there is a crosstalk between the design parameters, if we are not able to control a specific output by single input, then the current design is coupled. That means it is not easy for user, for customer, or for operator to control the system. It is a message to ideate on how to change the design, how to invent a new design. And in a new design, the user or operator is able to control each output by single input. If we succeed, and if the design is found, and it's cheap enough, simple enough, it meets other design constraints, then there are really good chances that the boss will say, "Good job." What is bad and what is good about axiomatic design? There are several conditions that the system must hold before this axiomatic design instrument can be applied. And one of the most painful conditions is that the number of inputs is to be equal to the amount of outputs, or amount of design parameters should be equal to the amount of function requirements, or the design matrix should be square, if you like. And if there are more inputs than the outputs, then we can call it redundant design. We'll try to simplify the design, to brush off unnecessary inputs. But it is intuitively clear that the less inputs, the better, the simpler interface. Then we can ideally control all the outputs by a single input. Or even more, they can control itself. That would come closer to ideal final result. That contradicts two axiomatic design prerequisites. Amount of input parameters should be equal to the amount of output parameters. The second problem is that the design is independent, but then we are not able to talk about system anymore, and I will explain you why it is bad. So in fact, we have to talk about a system that has been fallen apart in a number of independent subsystems, scalar input-output elements. That means that a failure of any of these subsystems will totally disable the control of this specific output parameter. The system becomes less robust, less controllable in this sense. Let us think of this water tap. That is independent, design is nice, but if the vertical handle is broken, we are not able to get any water at all, neither hot nor cold. While coupled, old-fashioned design will provide water in any case, whether left or right tap is broken. And finally, axiomatic design approach tells us where to go, but does not tell us how to go. Compare it to contradiction analysis of trees. We know that contradictions are bad in the design, but Altshuler gave a set of steps, a set of instruments to be used and how to use them in order to modify your design, in order to eliminate contradictions. Axiomatic design is coherent with other design tools, system analysis instruments like ideal final result or contradiction analysis from trees. And even better than contradiction analysis in these terms, that it allows us to work with more than two conflicting parameters simultaneously. The advantage of axiomatic design is that it works. Among other design tools, it really helps to meditate on how to improve an interface, how to improve a product or a system from user perspective. It gives us a reasonable design evaluation dimension from the perspective of usability and simplicity.